So having set up the variable slightly differently, we're starting to see failure happening now, and you can see it happening quite rapidly actually, which is maybe one of the reasons why we had such a slow loading rate initially. And you can see how very quickly it's just dived down there. You can see as well how the stresses are being channeled into the core, what remains of it. The core is making a bit of a comeback. Now once failure happens, it happens pretty quickly. So one of the options available to us actually is to do what we do for a stiff machine test, and for example monitor the displacements at the edge of the pillar, or we can monitor a number of different characteristics. I mean, we can see immediately when there's going to be a sudden when there's going to or when a decrease in the APS is starting to happen, and we can respond to that in the code. We can also run this as a series of solve stages. So we can put the velocity on for a little while, turn it off, solve, and repeat. Just keep doing that in the hopes of getting a more stable solution. Because this is quite a sudden failure that's involved most of the pillar. It is actually, as I say, it's making a comeback now. We're heading towards the residual state of the pillar where there's enough confinement in there to prevent any further failure. Oh, it's still 50-50 at the moment, deciding whether or not. Well, yeah, we see an increase in load, so it is starting to confine itself. And we see it happening there again. Yeah, it seems that the extent of the fracturing is kind of stalled as well. So we don't see clear, nicely delineated shear bands forming here. Going to mess up my outputs now. Yeah, this will mess up my outputs, by the way, by rotating the thing while the job is running. The next time it comes to the do plots command, it's not going to adjust the viewpoint back. So I'll get it back to roughly where it was before. But obviously you'll see that sudden change if you do if you try and animate this. One way of getting around that, just by the by, is this is continually reloading because it's being overwritten. One way of getting around that is to include these commands. The plot view, wada. You can just add that before you output each bitmap, and then you can be assured that you're going to get the same viewpoint every time. Previous versions of FLAC 3D had a serious problem in that they would suddenly, whenever they reached the end of a stage or did a plot, they would jump into the foreground. So you'd be typing away on something else, and then suddenly you would find that you'd adjusted the view because this thing had interposed itself into the application focus. That doesn't happen anymore, so it's not so much something you have to worry about. Yeah, it's pretty close to what it was. Anyway, we're not using these results for anything, so I'll leave it like that. You can see we're getting towards the end of our analysis now anyway, so it was reasonably well judged. I'm not sure if we have time. I think I'll leave it there for now, since I have to set up some other things in preparation for the lectures. As I say, one of the things we can do is monitor that the lateral deformation at the edges of the pillar, similar to what we do in a servo control test, and we can then control the velocity using a servo system. So, all right, that maybe is for homework, or if I can do it in the next half an hour, we'll do that. But for now, I'm just going to pause this. In fact, while we're waiting, I might as well put that history on. I'll only watch the one. Let me see, there's no preference for whether it's going to extend more in X or Y. So I'll just select one at random. I'll just say, okay, how about we have the X values. Or let me do the setup. I'll do it under here where I do the setup APS. I'll fact, I'll do a raw history here. I'll do a zone history. Zone history, I guess I want to look at acceleration. So what I'll do in a lot of these cases, and you've seen it here today as well, a lot of these cases you don't know what the perfect values are, or how to interpret, perhaps, or what values to enter as critical values. It's only once you've run the thing that you can look at the result and then decide. So I'll just set it up as acceleration in X, let's say. Fish history acceleration X, and then XYZ. Okay. Fish. Oh, sorry, wrong keyword. Zone history acceleration X. X and then XYZ, right? Okay. So it will be my sketch again in the X world. Yeah, it will be at XP 0 XP Y naught, and at my pillar center line, which is Z naught. Alright, now. Okay, one of the things that's worth doing is establishing how much difference there is in response to different loading rates. So what I'll do is load it twice as quickly, and first thing that I want the results to be stored somewhere else. So it makes sense to just change the name of this file as well. I'll just put v2 on the end. And remember, I must do the same here. This file doesn't know what its name is, or Flack and Fish don't know what the name of this file is, or where I want things until I tell it. So I'm changing my file root there, and I'm going to double the loading rate, which is contained here, top val. I'll change that to minus 2e6, and then we can directly compare what the results are by looking at this history output. So if I quickly look at the history output, Peleg APS, the most recent output, I'm actually going to copy that, plug it into Excel. Text to next space finish. Alright, so I should see the same thing I saw, very similar to what I saw above on the Flack screen. Yeah, very similar. You see there's a bit more compression involved there. So I can compare that with the result from the next run, which will just be pillar EG v2. Right. Okay. Zone history again. I need an example, so I'll just go here. Displacement Z position and then a vector. Okay, look. Okay, let's try that again. All right, I'll see you back here when it's done.